So I'm going to be talking about binary decisions that we make in integrity. And of course, these are everywhere, right? So we have to decide, should a post be removed for violating a platform's policies? Should an item be filtered from recommendations? Should a user's account be locked? All these binary decisions we have to make. And here the key policy choice is, where should the threshold be placed? And I say policy choice rather than a statistics or engineering choice, because this is not about how do we make the system operate the way we want it to operate. This is about deciding, what do we want the systems to do? There's a well-known trade-off here, of course. If we use a higher threshold, we take fewer actions, meaning fewer false positives, but also more false negatives. If we use a lower threshold, we take more actions, fewer false negatives, at the cost of more false positives. And one way to set these thresholds, or to think about this problem, is called cost-sensitive learning. So this is a well-studied approach. And what it does is it makes explicit that different decisions have different costs and benefits. And when I say costs and benefits here, I mean in the most holistic sense. I don't just mean dollars and cents. I mean everything good and bad that can happen when a decision is made depending on the true outcome. So I'm going to talk about a content moderation example here. We want to take down posts that violate some policy and leave up non-violating posts. So here on the left, we have our benign post that we want to leave up. And on the right, we have our violating post that we want to take down. So to start, we might say, well, first of all, it's costly to remove a benign post, right? That's a false positive. We have, deprived someone of their voice. And how costly is it? Well, the scale is kind of arbitrary. So we're going to define the cost of a false positive here to be 1, and everything else will be relative to that cost of a false positive. It's also costly to leave up a violating post, right, to make a false negative. And we'll say that the cost of a false negative is C. C is our cost ratio, and it means that false negatives are C times as costly as false positives. Another way to think about this is that C false positives are just as costly as 1 false negative. So that's what it means for a false negative to be C times as costly as a false positive. These are equivalent costs here, and we have C false positives and 1 false negative. And then once we have these costs, the way that we choose a thresholding policy is pretty straightforward. We want to choose the one that minimizes the expected costs. And you can do the math, and it's pretty simple. I haven't done it here, but we get a very simple decision rule. On the left here, we have the probability that a post is violating. And on the right, we have this fraction. And we want to take action whenever the probability the post is violating is greater than 1 over 1 plus C. So we have this term that only depends on the cost ratio, and it tells us where we should set the threshold, over what probability we should act to minimize our costs. To show this in a worked example, let's say we've got some sort of minor violation. We've decided that a false positive is 4 times more costly than a false negative. This means that the cost ratio is 1/4, so we should expect the cost minimizing threshold to occur at 80% when we plug it into the formula that we saw on the previous slide. Some of this has got a bit messed up, but you can still see. So here's our content ecosystem. We've got these posts here. Each post is marked with the probability that it's violating. These scores are calibrated, meaning that of these posts with a 90% score, 90% of them are truly violating. Of course, we don't know which 90%, that's the challenge. And we've arranged them at the top, most likely to be violating, down to the least likely to be violating. Let's take these posts one at a time, starting at the top. So we think about, do we want to take down these posts that have 100% chance of being violating? Well, if we take them down, we're going to make no more false positives, because none of them are benign. However, if we leave them up, we're going to make 5 additional false negatives for a cost of 5. And so the lowest cost decision here is to take down these posts. I think that makes a lot of sense. If you've got a 100% chance that post is violating, you should take it down. Now let's look at the 90% posts. Now, if we take these down, we are going to make 1 additional false positive. False positives have a cost of 4, so that's a total cost when we take them down of 4. If we decide to leave these posts up, we'll make 9 additional false negatives for a cost of 9. So again, the lowest cost decision is to take these down. Looking at the 80% posts, we see that if we take them down, we're going to make 1 false positive for a cost of 4. If we leave them up, we're going to make 4 additional false negatives, which is also a cost of 4. So here we come to a point where we're indifferent. The cost of taking down these posts and the cost of leaving them up is the same. And so this is the sort of break-even point where we want to set our threshold. Continuing to the 75% posts, again, if we take these down, we're going to make 1 false positive for a cost of 4. If we leave them up, we're going to make 3 false negatives for a cost of 3. So now we said that the highest cost choice is to take these posts down, so we want to leave them up. And just as our formula suggested, we found that it's cost minimizing, cost effective to take down posts with a greater than 80% chance of being violating, and cost effective to leave up posts with a less than 80% chance of being violating. So this way of setting thresholds by analyzing the costs of our decisions, I wouldn't say is the most common way that thresholding is taught both in educational materials and the classes that students take. And as a result, probably it's not necessarily the most common way of setting thresholds that I see in real integrity applications. Educational materials emphasize metrics like accuracy, F1 score, balanced error rate, while real systems tend to target either precision or recall. So we might say, I'm going to choose the threshold that achieves 90% precision because I think precision should be high in my use case, or I'm going to choose the threshold that achieves 80% recall because I think recall should be high in my use case. And I think taking a cost-sensitive point of view here can help us see why the challenges with these other approaches to setting thresholds that are more common out in the world. I've completely lost the pictures here, but we'll move on anyway. So I'm going to look at a course from Google here, but by no means is this the only place where you can see this this kind of material that ignores the cost of errors. So what they do is they look at a tumor classification example where there are 100 tumors to classify and 9 of them are malignant. And they have this candidate model that makes the following errors. It misses 8 malignant tumors, so it only catches 1 of them, but it also makes 1 false positive, right? Obviously 8 malignant tumors missed, that's pretty bad. That's 8 people who needed care who didn't get it. False positive is also costly. You know, someone gets scared perhaps that they're worried that they do have a malignant tumor. Maybe there's some additional treatment that was unnecessary. And the question that this course poses is, well, we've made 9 mistakes out of 100 decisions. It's an accuracy of 91%. Is this a good model? And in the course, they say, no, this isn't a good model because we can also achieve 91% accuracy with a model that predicts benign for every case. So it only ever says, it says everything is benign, and that also makes 9 errors, right? It misses all 9 malignant tumors, but it doesn't make any false positives. And the materials say, our model is no better than one that has 0 predictive ability to distinguish malignant tumors from benign tumors. Now, is this model really no better than the one that predicts always benign? I think the answer is no. The candidate model is better here. Why is it better? Well, it identifies 1 malignant tumor, right? That's 1 person who gets the care they need. And sure, it also creates 1 additional false positive, but a false positive in this sort of medical diagnosis setting is much less costly than a false negative. So we would prefer to have the candidate model as long as we think that false negatives are more costly than false positives, which I think is a very, very good assumption in this medical diagnosis setting. So it's not the case that the always benign model is no better. Actually, the candidate model improves here. And that's what a cost-sensitive mindset can bring to these kinds of questions. And if we take that mindset to look at these other metrics, we could look at accuracy. Well, accuracy is maximized with a threshold of 50%. And if we work backwards from our formula for the optimal cost minimizing threshold, we see that you get a threshold of 50% when false positives and false negatives are equally costly. So unless in your problem false positive and false negatives are equally costly, you shouldn't use accuracy. Notice that This has nothing to do with class imbalance. Often accuracy is taught as an inappropriate metric when there's class imbalance. That's not why accuracy is problematic. It's because it assumes that false positives and false negatives are equally costly. F1 score is quite strange. It's always maximized by a threshold below 50%. So it's always implying that false negatives are more costly than false positives. So if you're ever using it in a case where false positives are the more costly error, F1 score will give you some crazy result. And now I'll turn to the method of setting thresholds that picks a particular precision or recall. So maybe chooses the 90% precision threshold. And the reason why these fail is a bit more subtle, and it relies on analyzing multiple time periods or multiple segments of data, for example, different languages or different regions. So let's say we're choosing our thresholds to achieve fixed precision. We'll go back to our example content ecosystem here. So instead of using cost-sensitive thresholds now, we're just going to say we want to achieve 90% precision. And this is what our content ecosystem looks like in January. And we can see that to achieve 90% precision, we need to apply this threshold here. That gives us 20 actions, 18 of which are true positives. So we've got 90% precision. Now imagine the content ecosystem changes. And the particular way it changes is that we get a huge number of new posts to the ecosystem that are obviously violating. So these are posts that have a 100% chance of being policy violating. So maybe there are known slurs or things that we can otherwise identify with perfect accuracy as being violating. What happens to our precision now? Well, we've got a lot of obviously violating posts. Our precision at the old threshold goes up. We're setting our thresholds to achieve 90% precision overall. How do we respond to the precision going up? Well, we've got to lower our threshold. So now in February, after these additional pieces of content have been added, our new threshold that achieves 90% precision is down here at like 66%. Now, let's apply a cost-sensitive mindset here. And let's stick with the cost that we started with in the earlier example. So by lowering our threshold from where it was in January down to where it is in February, we've made 2 new false positives, 2 white posts there. Each false positive has a cost of 4, so that's an additional cost of 8. We've also made 5 fewer false negatives. We've caught 5 additional violating posts. Each of those, that mitigates a cost of 1 for each, so we decrease our costs by 5. And you can see that the net result of lowering our threshold here to target precision is that we've increased the costs by 3. So this was not the cost minimizing choice to lower that threshold. And I think that makes sense. Like we already knew what the cost minimizing threshold was. It's perhaps not surprising that moving it here increased our costs. But you might ask, what if we don't know these costs? People can often be hesitant or unwilling to put numbers to these different types of outcomes. How am I meant to compare the cost to speech of a false positive versus the cost to someone's emotional well-being of missing a violating post? And it's true. Now, it turns out that targeting a fixed precision is suboptimal no matter what the costs are. Right? It doesn't matter if we're unwilling or unable to specify these costs. All that is required is that if we agree that fewer errors are better than more errors. To show how this works, let's look at our ecosystem in January and February again. And we've got our 2 different thresholds that both achieve 90% precision in their respective months. And let's look at these posts here. These posts in January with 75% chance of being violating are below the threshold, so they don't get deleted in January. Whereas over here, we have posts with a 66% chance of being violating that are above the threshold in February, so they get removed. So we've got relatively high-risk posts in January. They're being left up, even while we take down relatively low-risk posts in February. What could we do instead? Well, we could apply a consistent probability threshold in both months in between those 2 precision thresholds. And we'd get a different set of policies. Now, what would happen? Well, in January, we would have lowered the threshold we'd make one more false positive and 3 fewer false negatives. In February, we've raised the threshold compared to the precision threshold, making 1 fewer false positive, but also 2 more false negatives. So on net, we've got the same number of false positives. They just cancel out. And we've got 1 fewer false negative. So we've got fewer errors overall. So no matter what the cost of errors, even if we can't specify them, we're better off here, aren't we? Because we just make fewer errors, same number of false positives and fewer false negatives. And this is true in general. Over time, as we continue to target a particular precision, we're going to introduce these inconsistencies that are going to lead to more errors than we would have had if we just applied a consistent probability threshold across all the months. Now, this has implications for fairness as well. So I previously had January and February as our sort of 2 segments of data. There's no reason it needs to be time. So instead now let's imagine it's Spanish and Portuguese, posts in 2 different languages. And similarly, the Portuguese content ecosystem has these additional obviously violating posts. We're setting our threshold to achieve 90% precision in Spanish and 90% precision in Portuguese. We get these 2 different thresholds. And again, we see that we have relatively high risk Spanish posts that we're leaving up, despite relatively low risk Portuguese posts being removed. Now, with a cost sensitive mindset, we can think about what would need to be true about our costs for these different thresholds to be cost minimizing. Well, the Spanish threshold is higher. For that to be cost minimizing, it must be the case that Spanish false positives are especially costly, more costly than Portuguese false positives, or Portuguese false negatives are especially costly, more costly than Spanish false negatives. So maybe Portuguese violations are especially bad somehow. But of course, all I've told you about this problem is that Portuguese has more obviously violating posts. So we've learned nothing about the severity or anything. But if we just naively apply precision thresholds, we get this unfair scenario where we're treating Portuguese false negatives as more costly, or Spanish false positives as more costly. All right, so I'm going to end with a call to action here. If your own systems are choosing thresholds to target a fixed precision or recall, I want you to go away and have a think about that choice, because you could almost certainly achieve fewer errors over time and across segments by using consistent probability thresholds. It can be calibration to find those thresholds, can be a hurdle, but in my experience, even noisy calibration will do better than trying to chase around the precision threshold that we know is suboptimal. And then if you're an educator or you work with educators, I would love to see machine learning and data science curricula emphasize taking actions. So we learn all about these algorithms to make predictions. We learn about all these exotic metrics, but we very rarely, at least in my training and my experience, talk about how do we translate those predictions into actions. And really, if we're not taking actions, what does it matter that we have, really accurate, really high AUC on our predictions? So the topics I'd like to see covered here include, of course, cost-sensitive learning, as I've talked about here, but also decision theory, welfare economics, the study of how we make decisions in a way that benefit individuals and communities and societies, how we aggregate welfare. That would be great background for our students to have, so that when they come and build integrity systems, really important integrity systems, they are equipped with the tools they need to make good decisions. Thanks very much.
Questions? Hello. Can you just talk a little bit about in practice, how do you calculate the cost? Yeah, like what's the thought process of
Yeah, it's a good question. And I think it's probably the reason why this doesn't happen more often in practice, is because it feels very intimidating to sort of put a number and say, well, actually, one false negative, if we miss a violating post, that's 193 times worse than taking down someone's post incorrectly or whatever the number is, right? A couple of thoughts there. One is that it really is a policy question. It really is a question of like, okay, what do you want your system to do? And so calculating it, you could appeal to different, downstream goals or downstream effects. But thinking of it as terms of something that can be calculated as opposed to something that we have to specify, I think it can be more productive to be like, this is just a parameter of what do we want our system to do, right? And that makes it a decision that has to be made with, the business mindset or whatever the context that you're doing. The other thing I'd say is that, in this example here, something like this, we're already acting implicitly with some costs in mind, right? If this is our ecosystem and this is Spanish and Portuguese, we saw before that this means that like a false positive is 4 times more costly than a false negative. And the 66% threshold means that it's 3 times more costly, or two times more costly. So we are already operating implicitly with costs. It's just that we haven't thought about them. And maybe if we thought about them differently, we would think, actually, that's too low or too high, right? And similarly, because we've got these 2 different numbers, we're acting as though errors are differently costly in these 2 languages. Well, maybe that's the case, but we actually haven't thought about costs yet. So maybe it's not the case. And so probably what will happen if we start thinking about costs in practice is that we realize we're already applying, costs are already implicit in what we're doing and our actions already, but we're being inconsistent about those costs. Maybe in one system, we're applying 10-to-1 cost ratio. In a different system, we're applying 100-to-1 cost ratio, even though it's kind of pursuing the same goals, right? And so that's what I think a cost-sensitive mindset can be productive here, is that it reveals potentially those points of tension or where we're not being consistent about our decisions across systems.
Any other question? I have one provocative.
Yeah, this is also more like a comment, because I'm thinking, so here, it seems you have 2 actions, so either taking down the account or not taking down. So I'm thinking if you have more remediation strategies, like, there's like shadow ban, like reCAPTCHA, so you can have a fine-grained the action and the different costs associated with that, and that may help further kind of optimize the best strategy.
Yeah, absolutely. This is purposefully the sort of most simple setting, but the same sort of mindset can be applied, to decisions where there are multiple fine-grained options. I've used kind of a linear cost function where like just every false positive is just as bad as the last false positive, but you could imagine, logarithmic ones or some way how we aggregate, where like, if you as a user see 1 violating thing, that's kind of bad, but if you see 10, that's worse than 10 times as bad because your experience is now flooded with violations. So once we start taking this cost-sensitive mindset, there's many, many directions you can go and many good things you can read about how to think about these costs.